So my name is Volker SORGE. I'm from the University of Birmingham, and we've just started a company which is called Progressive Accessibility Solutions. And the idea is that of the company is that we provide services around making STEM material accessible. And STEM, I luckily don't have to explain anymore because Betsy was talking a lot about it. So it stands primarily for science, technology, math, and engineering. And think about it this way. It's the skill. We need more and more people that have that skill, but less and less actually will have that skill because the education is going down. And that's at least the fear in the UK currently. And therefore, STEM accessibility is very important. And one of the major issues of STEM accessibility, of course, are diagrams. And I just follow up what Neil just said. And Neil said, images are bad, right? And we all know that. And images are bad, and I'll just repeat it once more, images are really bad. Because what images do is that they are not accessible, and you might have an alt text, but the alt text normally is very short because HTML, for instance, only allows you 128 characters, etc., etc. So unfortunately, what the reality is are images, right? Images exist and images are out there and images will stay with us for quite a long time, I believe. So one of the projects I've been working on over the last 1.5 years roughly is trying to make one particular sort of diagrams accessible and trying to make it accessible end to end, starting with an image, going all the way to a fully accessible diagram, which you can then voice or explore in any browser that you might have. And the particular type of images or diagrams I was looking into was chemical diagrams. And why chemical diagrams? Because chemical diagrams, in many ways, they are fairly complex. They're complex diagrams in the sense of what you find in the image, but they're fairly well understood once you roughly know what the chemistry is. And they have a lot less ambiguity than you would have, for instance, in some mathematics. So this is kind of the setting of the work I'm going to tell you about, and I'm going to extrapolate from that a bit, that this, I believe, is a way forward of making diagrams accessible in general. Now, there's been previous work on making diagrams accessible, obviously, and in particular, there's also previous work on making chemical diagrams accessible and making them useful for assistive technology. And the problem with all this work, in my opinion, is that it lacked the end-to-end component. So normally it would start out with some sort of an authoring a tool or authoring environment in which you could specify a chemical diagram or some sort of diagram. You would annotate it, and then a user would have to use a specialist reading tool in order to get to that. Right? And that, in my opinion, exhibits two flaws. One flaw is that we actually have to rely on authors, and authors being nice in order to use these authoring tools. And most of us are authors, most of us have written papers, and let's face it, we're all lazy, right? We all leave this for the next day. Right? Okay, now the paper is ready, I'll submit it, I'll make it accessible tomorrow. That day will never come. So in many ways, one thing I wanted to do is cut out the authors, right? Because once you have to rely on authors, you have to rely on a third party, which you can't rely on. And then the next problem is if you provide a specialist tool for people that allows them to access this particular type of diagram, then you just put another hurdle into their way of they have to now start up a new tool, have to learn all the commands that are attached to it, which might not be standard, and then have to actually operate in the tool. So in many ways, what the main idea of the work I actually wanted to do is that you start out with an image and you make that image accessible by providing a way of putting it into any ordinary browser so that it will work with existing assistive technology in a way that users ideally have a very, very limited new interface they have to deal with. And in many ways, the technology is there. We've been talking about it, or George in particular has been talking about it. It's HTML5. HTML5 contains everything that you need. HTML5, the spec is the same as the EPUB3 spec. So in many ways, you have everything there that you need. You have ways of making diagrams in a way that is scalable, where you can magnify things, and where you can actually walk through components in order to navigate something. Moreover, in HTML5, you have the ARIA specification, which allows you to actually then talk to screen readers, etc. And all this is what I'm going to use in order to make chemical diagrams accessible. Right, here's a couple of examples. I'm mindful that not all of you can see these examples, so I'm trying to explain them to you. One problem is you have to deal with, obviously, when you're not asking for authors to use a particular authoring tool, you have to deal with all types of possible diagrams they might give you. And already for chemical diagrams, there's a number of ways how you can display very simple molecules. And molecules, for instance, I have given a molecule example here, which is aspirin, everybody's favorite legal drug. And there's a number of ways how they are being displayed, and all three of these are from UK textbooks, from different levels, from GCSE all the way up to A levels. And there's a way where you can kind of spell everything out in a diagram where you have little dashes between atoms, like C atoms, carbon atoms, and oxygen atoms with O, and you have double bonds spelled out as 2 bars, etc. You can then, if you're a bit more advanced, you start omitting certain things. In particular, what you start omitting are carbon atoms, where you just, you just don't write those C's anymore. All you have, in a way, is a junction point in your graphic or in your diagram. And in addition, you omit writing things like hydrogen atoms. Because you're a chemist, you know roughly how many hydrogen atoms should be there if there's a carbon atom, so you don't do that anymore. Obviously, if you're not a chemist, that might be a problem. And then finally, you can even collapse that further by writing certain parts of a diagram just as a combination of letters, which effectively tell you what the atoms there are and how you can actually how they would be combined, right? Which only tells you something if you're really an expert chemist. Right. So the problem there is, in many ways, as you can see, if you have a diagram, you don't know the source of the diagram, you also don't know the level of detail that is given, and you don't know the level of expertise that is required in order to understand it. So you have to deal with all these subtleties there, and you have to, in a way, come up with a process that allows you to produce enough information on the diagram so you can deal with all those eventualities. Here's another example. Now, that's somewhat more complex. That doesn't even come from a textbook. It is, for those of you who can't see it, I'm telling you there's four different ring systems in there. There's some rings have sub-rings. There's chains and whatnot, and all kinds of different atoms. And it's rather horrible. It comes from a US patent application from 2002, right? If you have something like this, I feel that should also be made accessible, right? It doesn't really matter how simple or how complex the diagram is. You should be able to deal with all of that. Right, and I'm afraid now, for those of you who already think this is very technical, I'm becoming even a bit more technical now for the remainder of my talk, and actually to walk you through the steps of what you need to do in order to make these things accessible. And then hopefully give you an impression, first of all, how much work is involved, but secondly, how great it is to have that work done in the sense that it can be done now fully automatically. Right, so in a way, what I've been talking about motivates the whole procedure that we walk through. The first thing is you have an image, right? You need to first make this image. You need to be able to understand that image. The image is nothing else than black and white pixels, if you're lucky. Most of the time it's even worse. There's pixels in there that don't even belong to that image because it's artifacts from scanning. There might be a bit of dirt on your scanner or whatnot. Right? So what you need to do is first you need to do an image analysis and understand what are the parts of the image that are actually relevant to you and what do they mean. Right? Once you have that, you have kind of the big chunk done, but then you can generate something like an annotated SVG, which you can already chuck into a browser and you can make accessible this way. But it then turns out that all you know really are parts of the image. You know where there are lines, you know where there are letters, but you don't really know yet what they mean. So you then have to also try to find out what does that mean and how do I make this semantic available in a structured way that I can exploit it later. And how, by exploiting, I mean exploiting it by using some accessibility tool or just some means in a standard web browser that allows you to walk through a diagram and understand what the diagram means. All right. Right, I have 5 minutes and I have probably another 10 slides. So we're right. I'll be very, don't worry. I think the main part of my talk is motivating what we're doing rather than talking you through all the technical details. We've just won a Best Paper Award on that, I'll be proud to say. So be happy, you can all read the paper on this. Anyway, so what's the single steps are? The first step, as I said, is kind of an image processing step. And the image processing step, what it does is it tries to find out what we call the geometric artifacts in the image. Geometric artifacts are nothing else than, say, single lines, single characters, single circles, wedges, triangles, arrows, this kind of thing. So this is the first step you do. And after this image analysis, all you have are these geometric primitives. And these do not mean anything yet what they are actually in the context of the diagram. So they have no relation to chemistry yet. That's the next step, where you then start putting together things, the primitives that you have found, the lines, etc., in order to figure out what roughly is the chemical meaning of that. Right, so you're trying to figure out, well, if there are two lines close enough together, could they possibly be a double bond? Right, if there's a C atom, is there a C character, is that a carbon atom, or is there another dash next to it and it might be a chloride? Right, this is what you do. And you kind of then have a basic structural representation of your chemical diagram. And we use a particular chemical markup language for this, which is ChemML. And that's a fairly standard markup language. And that already gives you a kind of very basic semantic of your diagram then. Now, the problem with that diagram, once you have that language, you can already generate SVGs from that, right? Once you have that information. But that's normally not enough, because all that ever will tell you is where there is an atom and where there might be a bond. So all that you can do now is walk from one carbon atom to the next, and to the next, and to the next. Now, if you have a rather large molecule with, say, 50, 60 atoms in there, that's not very useful, right? So you then want to do actually some more serious work with your molecule. And in my opinion, with diagrams in general, you don't just want to know what the components of the diagrams are, but you also want to know what they really mean. And in chemistry, the way I do this is I identify certain substructures which have a certain chemical meaning. And these are normally called blocks, and they are normally things like ring systems. Think about it, back in your chemistry class, you might have ever seen a benzene ring, which is just 6 carbon atoms put together. There are things like functional groups, which are things like acids, esters, etc. And you then use these in order to combine them as a kind of a high-level overview of the structure. And that gives you a very then look at the diagram in case you can see it, then look at the diagram. But it gives you an overview of the molecule on several levels of abstraction. And these several levels of abstraction give you a very, very natural navigation model. And the navigation model, all that it does in a way is that you can view the molecule from the top as an overview, and then you can dive into it, walking along the molecule over those major structural blocks. And then if you feel like it, if you need more information, you can then dive into these blocks further and walk around these blocks if you like. Right? And how is all this realized? All this is realized by just putting it into standard web technology. So we're using SVG in order to represent the diagram. which then allows us magnification, it allows us zooming, it allows us highlighting of structures. We all embed this, so it's all standard HTML. We just have a bit of a JavaScript in the background, which just allows the navigation, and screen reader access is then supported by just using ARIA and ARIA live regions effectively. And right, and the navigation model in a way is a fairly natural one, as I said. And since the navigation model, in my opinion, is it's transferable. It should not only work for diagrams of a chemical nature. That brings me to the idea that what we want to do with these diagrams, first of all, we have a fairly generic basis in which that allows us to understand what an image is or what's in a diagram, which could be turned into other types of diagrams, not just chemical ones. And the navigation model in many ways would fit onto those as well. So as a future direction, I believe what one could do is look into diagrams, and we've already started doing this, which have a very similar structure than chemical diagrams. I'm thinking, for instance, about just basic geometric diagrams such as triangles, bearing charts, etc. Physics diagrams. There's always, whenever we went into schools in order to do some user testing and we went to the chemistry department, then the physics teacher normally would show up and say, can you do something similar for our physics diagrams? I have all these electric circuits, which are a nightmare to put down on what they call it German film in the UK. I think it's some sort of a tactile way of making things tactile. And obviously, once you have things in an electronic format of that nature, you can also make them automatically tactile. 3D printing is all of a sudden in your reach because you have a standard format. And the tactile images, in a way, once they're tactile, you can also link them to the spoken word, the semantics that you have given the image in the background. Thank you. I hope I didn't go too much over time. Thank you very much. Sorry, I will demo you what we've done with chemical diagrams. And this is an ordinary Chrome running an ordinary Chromevox. It's currently off of our online webpage even. In case that breaks down, I've got it locally. It works with other screen readers and on other platforms and with other browsers. So we've just tried it with NVDA and Firefox on Neil's machine just to have a backup in case, and it works fine there, and Safari, VoiceOver, and all these things. So as I said, the whole goal of our work is to make it accessible everywhere in kind of a standard EPUB or HTML5 format. I've tortured you with Aspirin earlier in my talk, so
Aspirin.png 799.
Thank you, Chromevox. This is the original image, right? So it's a very large one, but you can see it's an image.
Window undefined tab.
So you can't really do anything with this. And once I show you the web front end now, which actually allows you to browse that thing. And it's in a demonstrator, so you get a key underneath it to see actually what the key codes are that you can use in order to make it, to walk through it.
Explorer v0.4 example. Example 1.
Right. So here is already it's an SVG. So if I magnify that a bit, you can see. Oops. If I actually get
table.
Oops. Right. So if I magnify it, you can see it magnifies nicely. There's no checkies. There's no problems like this. And then
application.
You can just walk in there with the space. And it starts highlighting it, and it tells you it's an aspirin, right? In case, for those of you who, don't...
Aspirin.
Who can also see it on screen, you can get a subtitle going. And for those of you who are, with low vision, it's already difficult to see here. Let's change a bit the contrast. So maybe I always like it green on black. That's, for instance, how I normally have all my terminals and Emacs set up. Because it helps with contrast, so you can do this, and you can now start exploring it. And as I said, the exploration model is fairly natural, so we're trying to map everything just on cursor keys. So what you can do now is you can walk deeper into the molecule.
Benzene ring, substitutions at position 1 and 6.
Right, so now the benzene ring is being highlighted, you get it tells you there's 2 substitutions, which you can now start exploring as well. So you can walk now, in a way, we're trying to linearize this navigation, so that means that you now start walking these substitutions along the benzene ring.
Functional group ester.
You've got a functional group ester, and
Carboxylic acid.
you've got a carboxylic acid. And you might be wondering what this bizarre frame around that is. That is not our doing. This is Chromebox trying to highlight what the SVG is, right? So in other screen readers, that will not show up, for instance. In case you want, so you can now walk back up, for instance.
Aspirin.
You get back to the aspirin. What we can also do, you can switch on magnification for certain substructures.
Benzene ring. Substitutions at position 1 and 6.
And you can walk
Functional
around
group
there.
ester.
And you can walk back and
Carboxylic
forth.
acid.
And if you, obviously not if I know what a carboxylic acid is as a chemist, this is sufficient for me. Personally, I'm not a chemist. I always hated chemistry in school. I've now learned what all these things are, more by accident than by design. But for me, it would, for instance, be a lot better to actually being told what these things are in more detail. And you can kind of toggle an expert mode. I'll try that. And let's walk
Functional
back.
group with 4 elements COCOH3.
Oh, you get a structural formula. It tells you this is a functional group. And if you go back to say
Ring
the
with
benzene
6
ring-
elements. Substitutions at position 1 and 6.
Right, and if you're now even more curious and want, because you're really a beginner and you have no idea what a ring with 6 elements is, you just, you can start walking into that
Carbon
ring.
1 double bonded to carbon 6 single bonded to carbon 2 single bonded to functional group with 4 elements COCOH3.
Right, and you can now start walking around.
Carbon 2 double bonded to carbon 3 single bonded to carbon 1 single bonded to functional group with 3 elements COOH. Carbon 1 double
Sorry. Went in the
carbon
wrong
3
direction.
bonded to 1 hydrogen single bonded to carbon 4 double bonded to carbon 2.
Right, so you can now just walk left and right through your molecule. And the idea of the navigation model is that you now, at this position, you cannot get out of this particular block. It just tells you there are other blocks nearby, and you have to go back up in a way.
Ring
and
with 6 elements. Substitute. Functional
have to
group
go
with
into
4
the-
elements COCOH3.
And you have to go into the next functional group and then go back down. So you always know in which block you are at the time you're actually exploring that block. Well, these are effectively major things I wanted to demonstrate to you, just to demonstrate to you that this is not just restricted to one particular molecule or particular molecules you find in textbooks. I'll show you the other one. The one the slightly
Explorer
more complex one.
V 0.4 examples. US.
So this is, as I said, this is from a US patent application from 2002. It's from the 19th of March 2002. And again, this is the image that we analyze.
Explorer V's. Example 1.
This is the outcome.
Application. 1,4,1,4-fluorophenol. 1,4,1,4-fluorophenol. INDOL3YL. Butyl. Spiro 1H2BENZOFURAN3.
This is horrible, right?
4.
Just in case you didn't follow what it was trying to tell you here, I'll show you what this is as a subtitle.
1,4,1,4-fluorophenol. INDOL3YL. Butyl. Spiro 1H2BE.
So this is the actual IUPAC name, which we generate automatically off of a web service by the NIH, and I've tested that on chemists in Cambridge, and they had no idea what this thing is, right? When you give them this name, and so some of the rules that we've integrated into that system were then generated by actually talking to these chemists and asking these chemists to talk to each other over the phone, or rather, pretending to be on the phone and trying to explain each other how they would explain each other's structure of this nature. Right? And they can then come up with, they would start with explaining the major component. And the major components really in an order as we can walk.
Fused ring system of xylylene oxide with 2 subrings.
So this is it, that you explain the fused ring system and then you explain what is attached to the fused ring system.
Piperidine ring. Substitutions at position 1 and 4. Butane, substitutions at position 1 and 4. Fused ring system indole with 2 subrings.
And then you walk like this through the molecule, and again you can then dive into the molecule if you want to know more information. You can walk through the subrings separately, etc., etc. So that is it. And all this is live, it's online, and it should work with most assistive technology, with all browsers that support SVG. It works online. It works on mobile devices. I'm currently implementing some gestures for the exploration. And now, any questions, please?